when I was exhibiting at RCRS conference at Varanasi. So that time I got chance to interact with various scientists in astrophysics division, mainly in NCRA-TIFR. So Professor Amitav Sen Gupta sir and the sirs from GMRT, director sir Yashwant Gupta sir. And that time I was very much curious that we are RF people, means I was having background of RF and microwave engineering, and I was very much curious that to know that how the knowledge of this RF engineering is getting used for the application of radio astronomy and then detecting the planets and that galaxies and all that. So I was excited to know those things, and recently then from the same questions and the similar doubts, we come up with a solution that this kind of doubts will be there in most of the RF engineers' mind, so they can also get the answers of those questions. So we initiated to have a session which can give general idea about this usage of RF and microwave knowledge into astronomical field. So I hope this webinar is going to solve your curiosity and gives answer to your questions. So yeah, I would like to thank you again to the speaker for giving a glance or light on this particular topic. Thank you very much.
Yeah, thank you. So may I just request Shogoto, who is also incidentally today, it is his birthday. So he is one of our moderators. So happy birthday to Shogoto, and I ask you to just say a few words. You are also colleague of Professor Yashwant Gupta, so please say a few words.
First of all, thank you, Professor Professor Shoma Bhattacharya and Professor Yashwant Gupta sir, because I know what busy schedule he has. Okay. So first of all, I think Professor Yashwant Gupta sir, you don't have any introductory part for those who are working in the radio astronomy or any radio astronomy in anywhere in India or abroad or wherever you can go, anybody can know him. And it's my fortune, or you can say that I am the Almighty God give me this such an opportunity that I should work with the Yashwant Gupta sir, because I have closely worked with some doubts, and also when there is a doubt or something like that, I simply go to the sir, I have a few doubts, and he can say, okay, sit, I will clear your doubts and problems solved. So he is a person like, if you feel any problem, he can sit with you and so till he can sit whenever the problem gets solved. So that type of thing. I don't want to waste so much time. So Professor Shoma Bhattacharya and sir, Yashwant sir, you can start on it, and please carry on. Thank you, sir. One second.
Thank you, Shogoto. In fact, I also had done my master's thesis over there in GMRT, and I also have some kind of experience to work with him. And I know that he always encourages all the young people to work very hard. So let me just formally introduce Professor Yashwant Gupta. So Professor Yashwant Gupta obtained his MS and PhD in radio astronomy from the University of California, San Diego in 1990 after completing his bachelor's degree in electrical engineering from IIT Kanpur in 1985. Since 1991, he has been working at the National Center for Radio Astrophysics, NCRA Pune, of the Tata Institute of Fundamental Research, where he currently holds the position of the center director. Over the years, he has contributed greatly to the building and running of the GMRT Observatory, a world-class instrument built and operated by the NCRA and located about 80 kilometers from Pune. He also leads India's participation in the Square Kilometer Array (SKA) project, an international collaborative project to design and build the next generation global radio astronomy facility. His PhD thesis was on the study of propagation of radio signals from pulsars through the interstellar medium of our galaxy. His present research interests continue to be mainly in the area of pulsars, studying the details of their emission process and discovering new objects of this exotic species. Activities he continues to pursue actively using facilities such as the GMRT. He has over 100 papers in refereed international journals and conference proceedings. In addition to research in astrophysics of pulsars, Professor Gupta also has significant interest and involvement in instrumentation and signal processing applications in radio astronomy. Since the early days of the GMRT, he has made significant contribution towards the development of the complex digital back-end receivers for the telescope. Recently, under his leadership, a major upgrade of the GMRT observatory has been completed, which improves the sensitivity of the telescope by a factor of 3 and makes it a much more versatile facility. In addition, he also leads the technical involvement of India in the Square Kilometer Array. Professor Gupta was conferred to the prestigious prestigious Shanti Swarup Bhatnagar Prize in Physical Sciences for the year 2007. He has been elected a Fellow of the National Academy of Sciences of India and also of the Indian Academy of Sciences. So without further delay, I like to invite Professor Yashwant Gupta for his presentation.
Okay, thank you. Thank you, Dr. Shomak Bhattacharya, very much for the great introduction. Let me just confirm that you can all hear me.
Yeah.
Shomak, you can just confirm that you're able to hear
Yes, sir,
me?
we are hearing you.
We can hear you. We can hear you, please.
Okay, good. And you can see the presentation?
Yeah, we can see it. Okay.
Okay. All right. So a very good afternoon to everybody who is listening and watching. I'm not quite sure how many are present. I understand from...
Till now it is 79. Till now it is 80.
Yes, that is being... in addition to this particular meeting where participants are connected, is also being streamed live on YouTube and on Facebook. So I don't know how many are watching, but I hope that all those who are present will find this interesting. And as the title says, we will look at how we probe the universe using radio waves. And it will be a bit more from the engineering perspective rather than the astronomy perspective. So if you've been hoping that you will hear a lot about the astrophysics that we do, I'm afraid that will not be the case. We will be focusing more on how we do these things, because that was the main focus of this presentation. And I hope that you will get a good overview of how engineering is used in radio astronomy. And hopefully that will lead many of you, especially those amongst you who are still thinking about possible career choices, to look at this as one of the more exciting prospects that you could follow. All right, so, and as we discussed that, I'll take questions, but at the end, and via the moderators as they tell me. So please hold your questions till the end and we will deal with them. All right, so we will, let's start with a bit of an introduction. In fact, one would like to start from the beginning, tracing how astronomy started and how radio astronomy grew. And so I think, as most of you would know and agree, that astronomy is perhaps the oldest science. It started from the time we learned to look upwards and wonder what is up there in the heavens. And it obviously started with the use of naked eyes, because that is what the natural detectors for light waves that we had at that time. And all the signal processing that was done by the human brain. That itself taught a lot about what the universe is. But astronomy evolved dramatically with the invention of the telescope, which we know that it was this gentleman, Galileo Galilei, who in 1609 turned the recently invented telescope towards the heavens. Everybody else was using it for looking at objects on the earth. He decided to turn it towards the heavens, and lo and behold, it revolutionized astronomy forever, because all kinds of more detailed studies became possible. And in order to understand that, as to how telescopes revolutionized astronomy, we need to look at a little bit more as to what happened. So if you look at how optical telescopes grew through the ages, from the early telescope of Galileo to, so these are all models, the first few, to the one that Newton used for his studies, to what Herschel used, and then to the more modern observatories, which are all existing, the Mount Wilson telescope, the Palomar telescope, and then to these much larger, huge structures, some of which are actually under construction right now. And the message that comes through from these is that obviously bigger is better. And the simple question to ask is why? And that brings out two very interesting conclusions. One is something that you would think is fairly obvious, that the bigger telescope will collect more light. And if you collect more light, then you can see fainter sources. So it's just like when you go to a dim room, you dilate your eyes, the pupils become bigger so that you can admit more light and be able to see objects in the faint conditions. So this is the concept of sensitivity. So if you collect more light with a bigger telescope, the telescope is more sensitive. It can see fainter objects. There is another advantage of bigger telescopes. That is, the bigger telescopes provide a higher magnification. And what does that mean? That means that you can distinguish between nearby objects or sources in the sky. It is also called resolution. And what that allows you is to see more details within the same object. Okay, and the sensitivity obviously depends on the square of the aperture. That is the size, the total area of the telescope, because that decides how much light is entering. The resolution, on the other hand, depends inversely on the size of the telescope. This comes from the standard diffraction formula of optics, that the diffraction limited resolution is proportional to lambda, the wavelength at which one is operating, divided by the size of the aperture or the telescope, the diameter. So you can see that the bigger the D is, the more sensitive is the telescope, and it has a better resolving capability. That is, smaller the resolution means the finer details you can make out of any object that you're studying. And let us illustrate this with two examples. So this is a very simple example that we'd all be familiar with. So if you look at the moon with your naked eye, you would see an image something like on the top left. Just make out the disk. You can make out a few dark patches, but not much more. And you turn even a small, simple telescope towards the moon, then you can start seeing that, well, there are things called craters, bright spots, dark regions, and so on. And with more powerful telescopes, as you can see here, that you can now begin to see some of the fainter objects, and more importantly, you can start making out the detailed structure of what the surface of the moon looks like. We can take another example, and for those of you who do a little bit of amateur stargazing, you would have heard about the Andromeda Galaxy. It is one of the nearby neighbors of our Milky Way galaxy. It's located in the constellation of Andromeda over there in the sky. And if you look at this, if you go out in a very dark night, you can just about make it out with the naked eye, just as a very faint, fuzzy, small patch, a bit like this. But the moment you start looking at it with telescopes of small to modest to large size, you can see that both you can see fainter objects, whether they are nearby to the galaxy or within the galaxy, and you can also make out the much finer details of the structures that are present in the galaxy compared to what you could see just with the naked eye or with a very small telescope. So these are two very important concepts which drive us towards making bigger and bigger telescopes. Okay, now you can ask, well, that is good, that's optical astronomy. What happens beyond optical wavelengths? As we all know, that light or optical radiation is just one part of a very large range of radiation called the electromagnetic spectrum, which goes from the lowest frequency waves, which are the radio waves, to the highest frequency waves, which are the gamma rays. And here you can see that in this cartoon, where you can see the lowest frequency wave radio waves and the frequency increasing or the wavelength decreasing all the way up to the highest frequencies, which are the gamma rays. And just for comparison is shown the different sizes to which these scales correspond. And so the question you can ask is, can we see the same object in the universe at different wavelengths of the electromagnetic spectrum? And we'll see later on, yes, the answer is in general, yes. Then you would ask, do the different wavelengths give us different information about the object? And here again, in general, the answer is yes. And there is yet another third thing, which is that, are there some objects or phenomena which can be studied only at some particular wavelengths? And that answer is also yes. And so what that means is that if you could study objects at different wavelengths of the electromagnetic spectrum, you could either learn more about the same object by combining the information that you see. So it is a bit like when you go to the doctor today, he will do various kinds of studies, from X-rays to MRI to ultrasound and so on. And all of those probe different aspects of your body, and he will put that information together to try and make the best diagnosis. So in the same way, we can combine information from different wavelengths, if you can see the object at different wavelengths, and learn much better about what the object is and how it behaves and what is the physics. And the third point is important, that there are certain phenomena which can be seen only at certain wavelengths. That means that object does not radiate at all frequencies in the electromagnetic spectrum. And as we learn to look at the universe in different parts of the electromagnetic spectrum, we find that that is quite often true. And so that makes it interesting to be able to want to study objects at different wavelengths. So here is an example. We are back to our Andromeda Galaxy, whose optical picture is what we saw earlier when we were talking about the resolution and the sensitivity of optical telescope. But the same galaxy, when it is seen in ultraviolet or in X-rays or in infrared or in radio, does look different. So as you can see, different aspects of the galaxy become more prominent at different wavelengths of the electromagnetic spectrum. And this is what illustrates the power of being able to combine the information from different wavelengths. And so with that motivation, we can ask that what prevents us from going beyond the optical wavelength. And the one obvious answer is that you need the detectors. So as we said, that when optical astronomy started, we had the natural detectors in our eyes, but we don't have any other natural detectors. So we had to wait till technology developed where you could get efficient detectors. And so whether it is photographic plates or charge coupled devices or radio communication equipment, which allowed us to be able to receive the radiation at different wavelengths. So that is one aspect, and that is about technology. The second, which we don't often realize, is that not all the wavelengths from outer space reach us. And this you will all know well because of the ozone hole or the ozone layer. So that is the part of the Earth's atmosphere that prevents UV radiation, harmful UV rays from the sun to reach us. That means it blocks UV radiation, which means it will block any ultraviolet radiation coming from any object in the universe. And so, in general, the Earth's environment is not permissive to radiation from all parts of the electromagnetic spectrum. And this illustrates this in terms of the opacity of the Earth's environment as a function of the wavelength in the electromagnetic spectrum. And when you have zero opacity, means that the radiation can come through. When the opacity is 100%, that means that particular frequency or radiation will be blocked and will not reach the surface of the Earth. And so what you can see is that in addition to the optical window, which is in this range, which is the very narrow range of optical frequencies, the only other part of the electromagnetic spectrum, which is largely transparent, is the radio window, or a good part of the radio window. And so the others are blocked for some reason or the other, either due to molecules in the Earth's atmosphere which absorb, or the ionosphere of the Earth which reflects the very low frequency waves, and so on. And so you can then see that even if you had the detectors, you would need to also have satellites in order to put some of these detectors up in space before you can observe the universe in those kind of wavelengths. So the natural thing then you would think is that after optical, the next branch of astronomy that should have grown is radio astronomy, because that is possible to do from the ground the moment you learn how to make the detectors. And indeed,
Yashwant sir, I'm just sorry to just stop you over here just for a few seconds. All the participants are requested 1 second to please keep their video and audio off. Please don't make it on.
Okay.
All the participants are requested. Please.
So since you did, I just had one question. When I move my cursor, can people see that moving on the screen? If I show...
You move it 1 second?
Yeah, like if I'm showing different parts of the diagram, can you see the cursor? Probably not.
No, not yet.
Okay.
No.
Okay, maybe, how about now? No. You cannot see?
Yes, we can see.
Now you can
see? Yes.
Yeah, okay.
Yes.
All right, so maybe that means I should just keep it on the original PDF and it will show. Yeah, not on the screen. Yeah. Okay. So, and so the question to ask is, how did people learn about radio waves and how did they learn to make the detectors? So we'll do just a very brief recap. It was Maxwell who developed the theory that predicted that electromagnetic radiation could exist at all wavelengths, including radio. But it was a theory, and it was Heinrich Hertz who first proved that radio waves predicted by Maxwell do indeed exist. But unfortunately, he declared that there was no practical use of radio waves, having proved that they exist. And so it took these two gentlemen, Sir Jagdish Chandra Bose and Marconi, to actually demonstrate that you can generate and receive radio waves. And as we all know now, with the correct depiction of history, that it was Jagdish Chandra Bose who showed it first in Kolkata by generating waves at 60 gigahertz. But again, he did not go ahead and use this for any practical purposes, whereas Marconi realized the practical value of his experiments, and he went on to patent the work and to develop devices that would actually work using this principle. That is the first radio telegraphy sets. But to be able to detect radio waves from celestial objects had to wait for another 30 years. And this happened as a serendipitous discovery, as often happens, but just one moment again to pause to pay tribute to Sir J.C. Bose and his pioneering work. This is a diagram of the equipment that he used. We have a replica of this available at GMRT about the setup that he used, and there are some in other places in India also. So the detectors that we need came as an accident, as a serendipitous discovery during the 1930s as an offshoot of the development in long-distance radio communication technology. And their origin was in the Bell Labs, where this person, Karl Jansky, was given the job of testing and debugging transatlantic radio communication equipment that had just been built, which was suffering from some unwanted interfering signals, and unwanted hiss or pickup was being seen. And they could not understand where this was coming from, and it was affecting the quality of the transmission. And so he was given the job to debug and find out where it's coming from. So he built this contraption, which is actually the world's first radio astronomy telescope, which is a bunch of antennas mounted on a rotating platform, which you can see the wheels here. And he could then point it in different directions by rotating it around. And his aim was to search around and see where on the Earth this unwanted signal was coming from. And to his surprise, when he did this experiment, he found that the signal was not coming from any fixed location on the Earth, but it was coming from a fixed direction in the sky. And so you can see this little chart here, which shows the plots that he got, with the periodic bumps every time the antenna rotates to a particular angle. And he found that that angle was not fixed with respect to the Earth, but was fixed with respect to the direction in the sky. And so this then led him to understand that this radiation was coming from somewhere outside in the galaxy. And it was later confirmed that it is the first detection of a radio astronomy signal. And that is how the work in radio astronomy started. And originally, it was all done by radio engineers like Jansky. So this is Grote Reber, who is also an engineer in the Bell Labs. And during his spare time in his backyard, he built this instrument, which now looks a bit more like what we imagine when we think of a radio telescope, with a dish, with a reflecting dish and something at the focus, which is a receiver. And we'll talk more about these things in a minute. And this was operating at 160 megahertz. And using this, he scanned the sky in a systematic fashion and made what was the first radio image of the sky. And this is what that radio image looked like. So what this is a contour plot showing the intensity of the signal received by Grote Reber's telescope. And what it shows is that most of the strongest signals are coming from one particular band in the sky, which actually happens to be the plane of the Milky Way galaxy. And in that also, there are certain spots where the radiation is much stronger. And these are strong individual sources within the galaxy. So in fact, not all are within the galaxy. Some are outside extragalactic sources. So this Sagittarius is the direction towards the center of our galaxy, from which some of the strongest signals are coming. And so this allowed the work to start in radio astronomy to be able to detect the signals. And from then on, of course, the field has grown. But what became very clear from the very early days, that what we were getting was a complementary view. So this goes back to the question that certain objects would shine only in certain frequencies of the electromagnetic spectrum. And what people found very quickly is that what you see in the radio sky is very different from the optical sky. The brightest radio sources often did not have any significant counterpart in the optical, and vice versa. And so this obviously is very useful, because now you're learning complementary things about the universe. And here is one example which brings home the point that if you try to construct the general view of what a galaxy would look like in optical, then this is the kind of picture you would see, where you see a thin disk, which is the disk or plane of the Milky Way galaxy, with a bulge, which is the center of the galaxy, and not too much at distances away from the plane. But if you look at the radio image, reconstruct the radio image of the galaxy, you can see that it looks quite a bit different. And there is significant radio emission coming from much higher away from the plane of the galaxy. And this tells you that the objects that are being seen or the kind of sources are different. And that is because the physical processes that give rise to radio emission are very different from that of optical, and hence sources look very different in radio and optical. And thus radio astronomy gives us a new window to observe and understand the universe. And we won't have much time to go into the astrophysics as to why this happens, what are the physical processes, because that is not the main aim of today's presentation. We would like to go back to understand what are the tools of the trade of the radio astronomer. And so for that, we start with the basics for radio telescope. In a sense, it is no different from your satellite dish, which you use to receive your favorite signals of TV channels and so on. But there is a very major and fundamental difference, which is that the radio signals that we listen to are very weak. Actually very, very, very weak. And in addition to the fact that obviously there is always corruption due to noise that is generated either in the receiver system itself or picked up from outside, which makes it hard to detect these signals. So in fact, the signals are so weak that we have a special unit to describe the strength, which is 10 to the minus 26 watts per square meter per hertz, which is called 1 Jansky, in honor of Karl Jansky, who started the whole field. And if you want to understand what this means for electrical engineers, if you take an antenna of a typical modern radio antenna, with say about 1,000 square meters of collecting area and working over a reasonable range of frequencies, so you can then multiply by how many square meters and how many hertz it's working with, you will get a power which is minus 100 dBm. And as you all know, that 0 dBm is 1 milliwatt of power, and the dB scale is a log scale. So this is a very, very small amount of power that you are getting from a source which is of this strength 1 Jansky. And 1 Jansky is a very nominal strength of the radio sources in the sky. The other way to understand this, that with this kind of a typical telescope, over 1,000 years of continuously gathering the signal would collect only 1 millijoule of energy, which is again a very, very small amount of energy. So in order to overcome this, in order to now get the sensitivity, you remember one of the things we want is to be able to see faint sources, and already the normal sources are so faint. So we need to have very sensitive instruments, very sensitive radio telescopes. So how do you make it more sensitive? You obviously increase the number of square meters over which you can collect the signal. So you make as large dishes as possible, tens of meters in diameter, in some cases hundreds of meters in diameter. And that's about the practical limit. Secondly, as we said, that you try to observe over as wide range of frequencies as possible. That means you make your entire antenna, the receiver, everything work over a as wide range of frequencies as possible, because unlike man-made signals, many of these natural signals are broadband signals which emit over a wide range of frequencies. So you do as large a bandwidth of observation as possible. And then finally, in order to reduce the noise, which is what makes it difficult to see the weak signals, you try to build receivers which have high quality, low noise electronics by reducing the noise. And in some where necessary, you cool the receivers, because cryogenically cooling the electronics reduces the thermal noise that is present in any electronic circuit. Finally, in order to improve the signal to noise to detect faint sources, we can observe the source over long duration and integrate the data. So what happens is all these sources that we look at in the sky are statistically constant in their flux or in their strength, unlike again man-made signals which are continuously changing because you're transmitting information on very short time scales. A large number of the objects in the universe are pretty much the same today, tomorrow, next year, 10 years later, and so on. So you can carry out the observation of that object, following it in the sky for many hours and collecting that data, integrating it. So when you integrate, then the noise does not grow linearly with time. The signal grows linearly with time. The noise grows only as the square root of the time, which is a property of statistical fluctuations of noise. So you can improve the signal to noise and hence be able to see fainter sources with the same quality of noise in the receiver by observing for longer duration. So these are the ways in which we improve the sensitivity. So these all of these steps address that first problem of sensitivity. But there is this other issue, which I'll come to in a moment. So a typical antenna then that we use has these basic properties, which many of you would be familiar with, that you need a reflecting surface. It should be ideally a parabola, so that it can bring the radiation to a focus at a given point. That focus could be here at the primary focus, or you may choose to put a subreflector and reflect the radiation further and bring it to a focus at a tertiary point. Wherever that point may be, either at the primary focus or the secondary or tertiary focus, you need to put there an element which can convert the electromagnetic wave into a voltage. And that is a small antenna, typically a dipole. It can even be a horn antenna, which actually then is sitting at the focus, picking up that signal and giving you an electrical voltage, often in two orthogonal polarizations. And this antenna is, of course, characterized by the beam, the radiation pattern, whose width, which is the width of the main beam, which is the one that decides the resolution, because two objects within this beam in angular separation cannot be distinguished by the telescope. And this is the quantity that depends on the wavelength lambda and the size of the antenna d. Of course, the antenna needs to be fully steerable as far as possible, so that it can point to different directions in the sky, observe different objects, and more importantly, follow the object as the Earth rotates, so that you can observe the object for long durations. Okay, with that, we come to the next point, which is that how do we handle the issue of resolution? So as we discussed in the beginning, that the resolution is important in order to be able to separate out and see fine detail nearby objects. And it depends on lambda by d, as we discussed. And for optical telescope, that was fine because lambda is very small. But for a radio telescope, the lambda is much, much, much larger. So if you think of meter size antenna like this one, which is very large, fully steerable 100 meter size antenna is huge, working at 300 megahertz radio frequency, which is a very typical one, where the wavelength is 1 meter, then the resolution is half a degree. And half a degree is 30 arc minutes. That is the angular size of objects like the moon and, by coincidence, of the sun. Both subtend roughly the same angular size. That's why you get total solar eclipse. But what that means is that if you took such a large radio telescope and pointed it to the moon and it was emitting radio waves, you would just see one big fuzzy patch, just like even worse than what we see with the naked eye. And nowhere near what the simple optical telescope can give. And so here you have a problem. And this is a similar thing if you look at a galaxy, Andromeda Galaxy. If you did it with this simple single dish telescope, you would see an object which looks like this, nowhere near what resolution you would like to see the galaxy with. And so, this is the problem that radio astronomy faced in the early days because we're operating at much larger wavelengths than optical. And so these large dishes had their limitations. This is one of the largest ones, 300 meters in size on the island of Puerto Rico. But it is fixed, it can't be moved because it is so large. Similarly, now there's one in China which is 500 meters in size, but again fixed in the ground. So you can see the objects only when they pass overhead as the sources transit around the zenith with a little bit of movement, because this antenna which picks up the signal can be moved a little bit on the way it is suspended, but not too much. And so this problem required a novel solution, that in order to synthesize a telescope of much larger size, many individual dishes spread out over a large area on the Earth are used. And so this, the bottom figure here shows an example where you can see many, many antennas which are organized in a certain fashion. And it was shown by this gentleman, Sir Martin Ryle, that you can actually collect the signals from such an array of antennas and do a proper signal processing in order to effectively fashion a single antenna whose resolution is now not decided by the size of each antenna, but is decided by the largest separation between the antennas in the array. So if that is ds, the largest separation, then the resolution is now lambda by ds rather than lambda by d, where d would be the size of the individual antennas. And now you can see that it is relatively easy to have large separation between the antennas. As long as you have enough land, you can put them at large distances. You do have the challenge that you have to get the signal back from all the antennas and analyze it in this particular fashion that is required. But this really does work, and it revolutionized radio astronomy, so much so that Sir Martin Ryle was awarded a Nobel Prize for this discovery. And what it leads to is, in a bit more detail, is that signals from a pair of antennas, it acts like a Young's double slit. If those of you have studied the Young's double slit in your physics experiments or read about it, then Young's double slit acts like an interferometer, and it measures one spatial Fourier component of the image. So now if you think of the image as a two-dimensional intensity distribution on the sky, then you can do a two-dimensional Fourier transform, not a temporal Fourier transform, but this is a spatial Fourier transform, where the transform dimensions or domains are going from the angular size or the distribution on the image plane to the Fourier components that you can decompose that image into, and in 2 dimensions. It can be shown with rigorous analysis that the signal from any pair of antennas, when combined appropriately, can give you the amplitude and phase of that Fourier component, which corresponds to the separation between the antenna elements. So further apart the antenna elements are, the higher frequency components of the image they can measure for the same wavelength. It also depends on the wavelength. And therefore, when you have a range of antennas spread out, then by making different combinations pairwise of the N antennas, that is NC2 such combinations, you can measure NC2 Fourier transforms of the image. And then you assemble the image in the Fourier domain and then do an inverse transform to get back the intensity distribution in the two-dimensional plane. So this is the whole business is called aperture synthesis. You're synthesizing the effective aperture where the highest frequencies or the finest details of the image that you can measure is decided by the largest separations in the array. And this is the signal processing that you have to do for every pairwise combination of the antennas. That is, you have to bring the RF signal to a location where you may mix it to an IF or to baseband, and then do a correlation, which is a cross spectrum technically, and get the cross spectra, integrate them over a certain duration, store them on the computer, collect them from all such NC2 combinations, and then calibrate the data, and then do the inverse transform to get the image. It's actually more complicated than that, but in a nutshell, that is what happens. The important thing is that this oscillator has to be such that the phase at each of these two antennas, or when multiplying the RF with the oscillator, the phase has to be preserved. You can't have the phase of these two IF signals randomly jumping around. So these oscillators have to be locked, and this poses its own challenge, but all of these things are doable, and you can then actually get images of much higher resolution than is possible by the small individual dishes. And here is one example which shows an image of a particular radio galaxy, which has this kind of a structure. There is some emission in the center, and there is some clouds of emission at the two sides of the galaxy. And this is an image made before this kind of array instruments were there, with the best possible single dish of that time. And then later in the 80s, this VLA, the antenna array that I showed in the previous picture, became operational, and the same object, Cygnus A, radio galaxy, imaged with the VLA. And now you can see the difference by what is meant by resolution. You can see that the central thing is a very small dot of radio emission. It's actually the central core of the galaxy. And also you can make out this very narrow jet of emission. These are actually a very high-speed jet of plasma that is shooting out and hitting this part of the galaxy, and it is lighting it up. And you can see that it has a much finer structure. You can make out much finer structure than you can in the image on top. So this is illustrates what resolution can do and how high resolution is obtained. And just to say one more thing before I move on, that although you can get the resolution of lambda by ds, there are certain situations where the object that you may be studying is very compact and you can't resolve it by the array of even very large size. And there are such sources which we do have. And for example, that core of that galaxy that is just now showed, that central dot is very hard to resolve because it's a very small compact object at that distance at which this galaxy is located. But even within the galaxy, very small stars like neutron stars, which are only a few tens of kilometers in size, cannot be resolved with such with these kind of resolutions. And there, what we often use is just add the signals from all the antennas to make it look like a single antenna. This is what we do in a phased array, in any array of antennas when we make the concept that we use in a radar, or once we use in radio antenna arrays. So this principle is used in radio astronomy also. It's called array antenna or a beamformer mode of a radio telescope. And I won't go into the details of how it is done, but you can use it, and you can use it to study very compact objects in a more efficient fashion. Now, one question to ask is that we talked about this DS, which is the largest separation of antennas, and how large is it practical to make the separation? And we talked about, tens of kilometers as the extent of these arrays. But in principle, you can do this where you can have antennas which are located at hundreds of thousands of kilometers apart and are looking at the same object, working at the same frequency, and you can bring the data from all of them together and do that operation that I described, the signal processing. Then you can get very large baselines, that is this distance of separation between antennas, and you can get much higher resolution. So this is called very long baseline interferometry, and this can give you much higher resolutions, down to milliarcseconds, and to study very compact objects. You can ask, how is this done? How do you bring the data together? Because bringing the data together is almost requires a real-time operation. In the early days, the raw voltages from the antennas were recorded on disks, and then the disks were shipped to a common place, or tapes, or disks, and then played back, and then this correlation analysis was done. Today, it is possible with dedicated optical fiber links running from these antennas at remote locations to a central facility where you can bring together the data and do this operation in real time, just like it is done in the smaller arrays. And so this kind of thing is common. You can extend this with some more work to connect antennas simultaneously across continents, which is called intercontinental VLBI. And from there, you can make a jump of faith, but actually it's possible to do this, which is to have an antenna orbiting the Earth and be able to correlate the signal from that antenna with antennas on the ground. And now you have a baseline which is much more than tens of thousands of kilometers, and you can get very, very high resolution. But of course, it's a limited experiment because you can't have too many large antennas. At least today, it's not practical to have too many large antennas launched into space, but this has been done. It is possible. And these are some of the directions in which the future may move. But you can see what it does is it allows you to see that central core of the galaxy in much higher detail to make out what kind of jet of material is shooting out from the core of the galaxy. The other thing that the use of radio astronomy allows one to probe is something which excites almost everybody, is this question that in addition to these various sources that we see, which are all natural phenomena, which are emitting signals, are there some intelligent beings out there which are transmitting signals, just like we talk to each other using radio waves? Is there extraterrestrial intelligence that could be signaling to us using radio waves? And radio astronomy offers one of the best ways of trying to find extraterrestrial life by actually trying to look for radio signals. And I won't go into the details, but you can configure radio telescopes to do this. It's a very difficult task because you don't know what is the signal that you're looking for and what is its nature and when to say that I have found a signal. But a lot of time and effort is spent in observatories to look for extraterrestrial radio signals. And tied to it is this thing which I will not go into detail as to what is the probability that we are not alone, and what is the probability that a radio signal from some alien civilization can be picked up. So that's all a very interesting kind of thing. What I'll move on to is now to actually tell you what we do in India, what are our facilities, how radio astronomy has grown in India. And we will do that primarily by using our own giant Metre-wave radio telescope as a case study of a modern radio observatory. But just to trace back, radio astronomy in India was started in the 1960s by two groups. One in TIFR, that is in the institute where I work. NCRA is part of TIFR, by Professor Govind Swarup, when they built the first radio telescope in a place called Kalyan. Yeah, so this is the same Kalyan that we all know, a suburb of Mumbai. where today you will see only concrete buildings, but there was a time when it had a radio telescope located there. And then this group built a telescope in Ooty called the Ooty Radio Telescope, which is still functional, which we still use. And then our group built the GMRT in the 1990s. There have been other efforts by groups in Raman Research Institute, which built facilities in Gauri Bidanur near Bangalore, which is a very low frequency observatory using dipole antennas, and other facilities which have been functional over the years. In fact, India worked jointly with the University of Mauritius, collaboration from India and Mauritius, to build a telescope on the island of Mauritius, which ran for a few years. So talking more about the GMRT, it is a low radio frequency facility. So as I showed, that radio window, which is open from ground-based radio telescopes to observe the universe, is quite wide. It goes from about 30 megahertz to about 300 gigahertz. And so no single radio telescope can really cover such a large range of frequencies. And radio telescopes today are built to specialize in different parts of that part of the electromagnetic spectrum. So our telescope focuses on the range from about 100 to 1450 megahertz. And in this range, it is one of the largest and most sensitive radio telescopes in the world today. It consists of 30 antennas, 45 meters diameter. You can see pictures of some of the antennas, and I'll show you in a minute what the configuration looks like. It was built, designed and built indigenously in the country during the 1990s, and it's operational since 2002 as an international facility used by astronomers from all over the world. And recently in 2018, we completed a major upgrade, which has made it a more versatile and more sensitive facility than it was in its original design. So this is what the array looks like. The 30 antennas are spread out over a region which is roughly 30 kilometers in diameter. And as you can see, again, it's a roughly Y-shaped structure with 3 arms going out to a bit over 14 kilometers. And in the center, in a 1 kilometer by 1 kilometer region, are the 12 of the 30 antennas. And so it's located about 80 kilometers from Pune. So this is the Pune-Nasik highway. If you travel from Pune to Nasik, you will pass right through the GMRT array. And you can stop by and visit. You're welcome to do that. We encourage visitors, though not all the time. There are certain fixed slots, but you should get in touch with us if you would like to visit. This is what it looks like, seen by Google. Today, everybody wants to learn everything from Google. So if you Google, this is what you will see. This is that central 1 kilometer by 1 kilometer amidst lots of farmlands and so on. And you can just make out the individual antennas in this Google image. You can zoom this and you can make out a little bit more detail. You can zoom it further. These are the 3 nearest antennas in the array. This is a view of the receiver room and the control room. So all of the work that happens in this building, which receives the signals from all the 30 antennas over optical fiber and converts it back into a voltage signal. And then all that processing that I described, whether to do the cross correlations or to make the beamformer, are all done in hardware, which is located here. There's a control room from which you can control the entire array, set up everything and run long observations. And all of that is possible without any interaction directly. Just one person on duty can run the entire observatory and carry out the scheduled experiments. So just show a few pictures. This is a picture of the same central array taken from a nearby hill. This is close up of one of the antennas, and now you can see what it means, 45 meters diameter. It is a 32-meter high platform, which is required in order to reach the focus of the antenna and to do any work there, whether it is to put new electronics or to repair things and so on. One of the interesting things that you may notice is that this looks like the antenna is transparent. There's no reflecting surface. Actually, there's a very fine mesh of steel wires mesh, which is there, which acts like the reflecting surface, which is good enough for the frequencies of interest that we work at. And so this is, you can see that the complexity of building such a structure, the tower on which the antenna sits is equivalent of a 3-story building. And then on top of that, the antenna is assembled piece by piece. And finally, the full antenna is ready, and the 30 such antennas in the array. As I was saying earlier, that this was built during the 1990s, and towards the end of 2001, it was formally dedicated with a formal launch ceremony. And from 2002, it was open for people from all over the world to use. So it is now TIFR. And so if you can ask who all uses it, pretty much people from all over the world use the GMRT. You can see here the ratio of people from India, that is from Indian institutions who lead the experiments, about 50%. And the remaining 50% are astronomers and investigators from many, many different countries in the world, from some of the best places where astronomers are working. And it is highly competitive to get your experiment scheduled at the observatory. So the way it works is that we take proposals from all over the world twice a year, 6 months apart, and anybody can submit a proposal as to what they would like to use the facility for, what kind of science, and the proposals are rated based on their quality, that is the impact, what kind of science they will produce, and they are then refereed by a committee which decides which ones should be given time, what is the priority, and then we schedule those particular observations which have been selected for the next almost 6 months duration. And the competition is very heavy, which means the total amount of time that we have available for users to schedule experiments is typically 2 to 3 times less than the total number of requests that come, the total request for number of hours of observations. And so this is a situation where demand is more than supply. And so whenever that happens, there is competition, and only the best proposals are then allowed to be scheduled on the telescope. And what do these proposals do? There's a whole range of science which can't go into the details in this presentation, but you can study the sun. You can even look for planets around other stars using radio signals. We know that Jupiter emits radio waves, so you can see if you can find Jupiter-like planets around other stars, to studying neutron stars, to looking at different galactic objects like supernova remnants, microquasars, and explosive transient events like gamma ray bursts, and then looking at various hydrogen gas in various forms, because hydrogen is one of the most pervasive elements in the universe, the most abundant element, and every part of the universe has large amounts of hydrogen, and that is very easily detected in radio waves. In fact, the hydrogen emits signal which can be seen only in the radio waves, and that's one of the unique properties. And from there to various kinds of galaxies, to looking at very early phases of the universe, how it formed, how it grew, how it evolved, to making all sky maps of the entire universe, like an atlas that you would make, showing the different objects that you can see in a uniform manner. And like an atlas is used for various reference studies, these kind of surveys are used for various reference studies by astronomers. And so typically there are more than 50 papers per year that are published using data from GMRT by people from all over the world. Now, if you would have gathered by now that in order to make a facility like the GMRT, you need engineering expertise, not just in radio engineering, but all kinds of engineering, from mechanical to build such large structures in a cheap and efficient manner and make them stable, to the servo system, which was moving these antennas in a very precise manner to point them in different directions in the sky or follow objects as the Earth rotates, to the actual radio frequency engineering, which starts with the antenna feeds, which need to pick up the signal over as broad range of frequencies as possible, and then the very high quality low noise amplifiers which need to amplify the signals without corrupting them by noise, and then bringing the signals down, transferring them from the antenna location to the central building over optical fiber. So there's a lot of optical fiber technology that is used, and then finally bringing the signal down to baseband, digitizing it, and then doing the rest of the processing in digital domain. And that is a fairly intensive technology and hardware that is required. On top of that, you need a lot of monitor control and telemetry technology distributed over the 30 kilometers so that you can control each and every antenna, each and every aspect of the electronics. You can set what frequency you're observing. You can set every parameter from the control room and monitor the status of everything. And so a very sophisticated software for monitoring and control, running the observatory in a coordinated manner so that you can do long, 8-hour-long observations following some source in the sky with a certain specific sequence that the astronomer wants. And finally, the ability to be able to process all of that data and to make that technique that I described as to how the images are made. That is a fairly sophisticated signal processing and computing that is required before you can get the final result. So that's a wide range of engineering topics, and I'll just very quickly talk a little bit about the receiver system. So typically it looks like this, that you have this feed antenna that I mentioned at the focus, which is either a dipole antenna or a horn antenna, but it is dual polarized. That means it can pick up 2 orthogonal polarizations. And then it goes to this front end electronics, which has low noise amplifiers. And then it is brought down by cables to the antenna base, where there is further electronics amplifying it. And in the older system, we used to convert it to an intermediate frequency by using local oscillators, and then transmitting those intermediate frequency signals for both polarizations over optical fiber, receiving them in the central building, and then converting them back to analog voltage signals, then digitizing them and doing all the digital processing. Today, we do this with a maximum bandwidth of 400 megahertz, whereas the original system had a 32 megahertz bandwidth. And this is a signal processing view of that, where what are the different signal processing steps you need once you digitize the data. You have to correct for the different delay paths of the signals coming from different antennas. And then we take a spectrum by doing a real-time fast Fourier transform. This is the traditional temporal Fourier transform. This is not the two-dimensional Fourier transform that I was talking about earlier. This gives you a spectrum of the signal from each antenna, and then you do further phase corrections, and then you give it to this, which produces the cross spectrum, or you can add the signals, as I was explaining, in the single dish mode to form the array beamformer. And these outputs are then integrated over time for a certain desired duration, and then recorded on hard disks for the offline post-analysis. So this thing is like a 15 teraflops of computing running real-time 24/7 with 20 gigasamples per second input data rate that it is handling. And so the GMRT, as I mentioned, this has been producing lots of interesting new results since 2002 that it was released. And we completed an upgrade, which was formally inaugurated in 2019, but it has been available for use from 2018 onwards, which has improved the sensitivity by up to a factor of 3 and allowed a much wider range of frequencies to be covered, which makes it a much more versatile facility compared to the original version. And this then keeps it as one of the most sensitive facilities in the world today. And these are some of the details about the original GMRT was the upgrade. This shows the improved sensitivity of the GMRT. It's a bit technical, so I won't go into the details. It compares it with other facilities in the world and shows till the next generation facility like the square kilometer array is built, the upgraded GMRT will be having the best sensitivity, where sensitivity is measured by how much noise remains in the image finally. That is, what is the weakest signal that you can see in an image. There is one interesting aspect which is worth talking about, that when you have such a sensitive telescope, it can pick up different kinds of radio signals, which need not be just the astrophysical signals that we talk about. And often such facilities are used for joining in some of these space exploration exercises. And this is one example where we use the GMRT, working in collaboration with NASA and ESA, the European Space Agency, for providing ground support for tracking one of the space missions to Mars, which was going from the European Space Agency called ExoMars. This was back in 2016, where a bit like the Chandrayaan thing that we all watched, where there was a lander module which was there, which separated from the mother spaceship and was trying to make the landing on the Martian surface here, using this combination of parachutes and then the thrusters to slow it down and so on. And our job was to track this. It was emitting a beacon at 401 megahertz, which is like 3 watts of signal from Mars. So it's like if you went to Mars with your mobile phone and were talking, then we could pick up that signal. And so we were able to pick up the signal and follow the Doppler shift of that frequency as the object went through its motion to try and make that landing. But unfortunately, a bit like Chandrayaan, this was also unsuccessful. It crashed at the last moment. It made the journey, most of the journey safely, the 7 or 8 minutes, but the last 40 seconds, things went wrong and they could not control it, and it actually crashed on the Martian surface, a bit like what happened to Chandrayaan 2. So at this point, I can take a summary. I have a little bit more material, which is looking at the future projects in radio astronomy, but I will ask the moderators to see whether we can go. So, Shomak, what do you say?
Yeah, please continue. Please continue.
Okay. So then there's a final summary. I'll do it there.
Yeah. Please continue. Then I will take questions.
Yeah, just a few slides on what the future is.
Sure.
So we talked a lot about GMRT as being one of the modern facilities, one of the most sensitive and largest facility today, but there's already plans to build much larger facilities in the world. And amongst the one that is of most interest to radio astronomers is what is called the Square Kilometer Array, which is truly a next generation radio astronomy observatory. It just finished the design phase. We spent last 5-6 years building the detailed design for this radio observatory, and phase 1 of the construction will be from 2021 to 2027. It's delayed a little bit because of all this COVID-19 pandemic has slowed down the work, but hopefully it will pick up by later this year. And it's a huge observatory. So if you compare it with if GMRT was built today from scratch, it would cost about this much, 500 crores. This is something which is of the order of €1 billion total cost. It is to be located in a very radio quiet region. So one of the biggest enemies of radio astronomy is man-made noise, man-made radio interference, and which is not very good in the location where GMRT is now because of the growth of industrialization and growth of human population, which is there everywhere in India. But in places like the desert areas of Western Australia or in remote parts of South Africa, there are still sites where you have very little man-made interference from ground-based systems. And these are the locations where the SKA will be located. And it'll have a headquarters, which is in the United Kingdom. And it's a global alliance of already now more than 10 countries working together. India has been part of this from the beginning. And so it is split into 2 parts. SKA, what is called a mid-frequency, which is frequencies which will be from around 300 megahertz to about 10 gigahertz, using dish antennas, but much smaller dish antennas in GMRT. These are 15-meter kind of size of antennas. But the final configuration, phase 1 will have about 200 of these antennas spread out over 150-kilometer region. So you can compare all these with the size of the GMRT and its extent, and located in this part of South Africa, which is a remote place where you count number of people as 1 person per square kilometer or half person per square kilometer kind of population density. And similarly in Western Australia, again in a remote location, this is a different kind of telescope. It is a low frequency telescope which will work from something like 30 to 300 megahertz, and its design will use dipole antennas like this, of the kind shown here. So farms of dipole antennas called stations, something like 1,000 dipoles in a station, and then something like 500 such stations, again spread out over a 80-kilometer region. So total of 128,000 or 130,000 dipoles, each with its own low noise amplifier, and then a way to collect the signals from dipoles at the station, and then take data from stations to a common place for the common analysis. So this is what the international collaboration looks like. Different member countries who are working together. Others who are interested in joining, some have already joined, like Portugal recently, Germany's close to joining, and so on, Switzerland also, and working all together with the common headquarters in UK. And so this, as you can imagine, that in order to build something like this, you will be really pushing the technology in different areas. As I showed, different kinds of antennas, from the traditional dish antenna, but this is also not very traditional. You can see it's an offset Gregorian, and to these farms of dipole antennas, very diverse design principles. And here, at least for the dish antennas, all the amplifiers will be cooled, gradually cooled to reduce the noise temperature. And you can imagine, we talked about fibers from GMRT antennas to bring the signals to a common station. Here, this will be a very extensive fiber network with the total traffic of petabits per second, which is more than the total internet traffic today. And to analyze all this data, process it, supercomputing equivalent petaflops to do this processing, and to manage this all and make it work like a coordinated observatory. Very sophisticated management and control software will be required, which is one of the areas where India will be taking the lead. We have done the design for this, and we'll be leading the construction of this, along with participating in other parts of building the telescope. And finally, when you want to process this data, you are in the regime of, you hear today, big data, right? Big data is a big buzzword. This is one of the biggest data machines that will be there. And all kinds of tools, from artificial intelligence, machine learning, and all kinds of modern techniques will be needed to the hilt in order to be able to really process this data in a meaningful fashion, because the amount of data it will generate will be huge. And so that, and I didn't have that slide, the kind of science it will do will be fantastic. It will be out of the world, much, much better than any facility in the world today. And that is what the radio astronomers are looking to. In fact, all of the astronomy community is looking for this next generation leap in the radio astronomy capabilities. So with that, I've given you a quick tour, starting with the very basics and what are the principles behind the radio telescopes that we build, and how radio telescopes came into the picture, and what kind of techniques that we use in order to achieve the goals and targets, specifically the sensitivity and the resolution. And we showed some of that by going in more detail into how the GMRT works like a world-class low-frequency radio astronomy facility. And we talked about how it's been upgraded to keep it on the forefront for next several years. And we talked about the long-term beyond those next few years, which is a decade and later, is the square kilometer array. And also we touched upon other aspects that sophisticated radio observatories can be used for other purposes, whether it for space exploration experiments or for searching for extraterrestrial intelligence. And so that brings me to the end. If there are questions, I'm happy to take those up for discussion. Thank you.
Yeah. Thank you, sir, for such a nice talk. In fact, let me first open to Shogato. And actually, Swapnil had some internet problem. He just messaged me, so he had to go offline. Shogato, did you get any kind of questions from Facebook? So first you narrate, then let me narrate the questions what I have received here.
So first you start, and then I can take the questions.
Yeah.
From Facebook. Yeah.
Yeah. Just 1 minute. Yeah.
Yes.
Yeah. So, sir, the very first question that what I have received over here, that one has asked that, so we have to synchronize every antenna's clock, or so they work, so they can work at a simultaneously at the same time?
Yes. Like I was saying, if you are using a local oscillator to convert the RF signal to an IF signal, which traditionally was done, and nowadays we bring the whole RF signal back to the central observatory, then you have to send the local oscillator out to each antenna, and it has to be phase locked you can't lose the phase. Secondly, when the voltage signal comes to the central station, when you digitize it, the digitizing clock has to be common for all the antennas that are being digitized, and you can't afford to have variable jitter between the clock that is digitizing the signal from different antennas. That has to have a fixed relationship. Right. There can be small delays, but they have to be fixed. You can calibrate those delays, but you can't have them varying.
Yeah. So the next question what I have received, that did they identify any particular source later on for the very first celestial radio waves observed by Jansky?
Yes, so that is actually the center of our galaxy. The center of our galaxy is a very active region where there is a very large black hole at the center of our galaxy, and a lot of material or mass around it, and a lot of activity happening there, which produces very strong radiation. And it definitely produces radiation in optical as well as other wavelengths. But what happens is, because there is intervening gas and dust in our galaxy, the optical waves get blocked and they don't reach us. Whereas the radio waves can propagate through the dust and the plasma that is there, and they reach us. And so the radio provides a very good way of probing the center of our galaxy.
Yeah. The next question what I have received, that are there any plans to add a transmitter capability to the NCRA telescope in the near future?
No, for NCRA, we don't have plans to add transmitter facilities. Very few of the radio astronomy facilities have transmitting capabilities. The only ones that have it are, like I showed that large dish, fixed dish in Puerto Rico, the Arecibo Radio Telescope. It was designed to be a radar also. So it actually sends radio beams which are bounced off the asteroids in the solar system, and it is used for studying details of asteroids by literally the radar technology. But that's about it. There are hardly any other radio telescopes which actually transmit.
Okay. And another one has asked how to differentiate the object of observation from others in the whole galaxy.
Yes. So in order to differentiate objects, you need to either be able to separate them out spatially, which means that if there's any nearby object, you can see them as different objects. And that is where that issue of resolution comes in. Your instrument should have enough resolution so that you can separate out two spatially nearby objects and say that, well, this is object 1 and this is object 2. Once you separated them spatially, then you can ask, is object 1 nearer, is object 2 further, and what are their different properties. But as long as you can't separate them out spatially, then you can't make out. That is one issue. The other issue is that in some cases, by the fact that different objects emit differently with different properties, then you can distinguish between two nearby objects or two objects which otherwise you're not able to resolve by the fact that they emit different kinds of signals. So there's a combination of these kind of things that we use in order to distinguish between different objects. Sometimes it is not possible to do that, and you have to live with that uncertainty and try to interpret as best as possible given the ambiguities.
Yeah. Then I have received the question how to calculate the beam formation to measure the target.
I'm not sure if I understand that question, but in order to do beam formation, so the aim of any beam formation is to produce a narrow beam from combining the signals from an array of antennas so that the beam is directed in the desired direction. And what that involves in any array antenna, in order to do that, you have to combine the signals from the individual antennas with appropriate delays and phase shifts. Yeah. That is how a beam is steered, whether it is a sonar beam or a radar beam or any other beam. You steer the beam to the desired direction or the object by adjusting the delays and phases of the signals that are being added from the different elements of the array. And that is what is done here. The principles are reasonably straightforward. Practical implementation varies depending on the actual practical issues or difficulties.
Okay. Then I have received the question, how to design a feeding network for such a large size array?
Design a feeding network.
Feeding network, yeah.
Yeah, so once again, I think that whoever has asked the question is again thinking about a transmitting case, but maybe they are thinking about receiving case. But yes, that network is, like I said, in the early days, it used to be cables that used to come back from the elements of the array, bringing the radio signal back, and then you would have the appropriate way of combining those signals. Today, as I said, the signal, whether it is a RF signal or an IF signal, is modulated onto an optical fiber. The optical fiber then carries that signal to the final destination. It is demodulated back to voltage, and then you mostly nowadays you digitize it as quickly as possible after maybe down converting it to baseband or filtering it a bit or whatever. And after digitization, then you combine that the signal in the desired fashion in digital signal processing in order to get the final output. I don't know if that answers the question. It's not very clear what do they mean by network.
Then the next question is how machine learning is useful in radio astronomy.
Well, that's an interesting question because it's a relatively new development, but there are at least 2-3 different kinds of areas where it is used. One example is that often when we see different kinds of sources, and now with the sensitivity of the instruments, you can see lots of sources. So, for example, you can detect hundreds of thousands of galaxies in a field of view, and then you need some automated way of saying this is a galaxy or this is not a galaxy. Or you need an automated way of saying that this galaxy is of this kind. And, you know, there are classifications of whether a galaxy is like a spiral galaxy like the Milky Way or elliptical galaxy. And there are more finer classifications. What kind of spectrum does it have, and so on. And similar thing you can think of for the thousands and thousands of stars that one can now detect in astronomy in general. I'm just not talking about radio astronomy now. And so there are these detection classification schemes or scenarios where machine learning has proved very useful. There's also this situation where discerning between a real signal and an artifact due to noise is another situation where machine learning is used is beginning to be used very frequently. And so there are these currently these are the kind of applications, but every so often we find new areas where the concepts can be applied, and really it's up to the ingenuity of the people nowadays to see where it can be used.
Another question, sir, I have received that apart from Hubble Deep Space, any other space instrument that facilitates the clear spectrum to see the massive UV Scuti and Canis Major is the supergiant massive stars in galaxy?
So I'm not sure again what.
Yep, can I read it? Apart from Hubble Deep Space.
No, I heard the question. I'm just trying to understand what they're wanting to know. So, for example, there are lots of different spaceborne observatories. I didn't show those slides in this talk because I wanted to focus on radio astronomy, which are observing the universe in optical, infrared, ultraviolet, X-rays, gamma rays, and so on. So, you know, you may have heard of some of them like the Spitzer telescope. The Hubble happens to be the most famous because it has been taking very nice optical images and studying objects in the optical for many decades now. But the other ones have been there, which has done similar work in infrared and ultraviolet and so on. And so they are all capable of observing different kinds of objects. Now, the specific ones mentioned, I'm not sure whether which all facilities can observe it. And there's a successor of the Hubble planned, as you all may be knowing, the next generation version of Hubble, which is getting ready and will be launched in a few years.
Yeah. Another question has come from the same person. The solar Parker developed in NASA to see the movement of sun plasma spots and magnetic fields. Which type of antennas are installed which sustain such enormous heat from the sun?
Okay, I'm not sure if I know the answer to which type of antennas, but the way the space technology works is there is a lot of work done in order to make whatever you put up in space to be space qualified as compared to things that we put on the ground. And that is a completely different quality or league of what is built.
Right.
But I'm not exactly sure of what is done in the Parker probe and specific things.
Yeah. Another question is the large number of dipoles are used as an antenna array element and they are on Earth's surface. These are not like linear or circular array. And also, what is the spacing between them?
No, so it can be made as a linear or circular array. So what you have to think about is that, like I was saying, that the dipole antennas are arranged in first cluster is a station of dipoles. In a station of dipoles, it is like an array of dipoles, and it will be used to form a particular beam in a given direction in the sky. So you think of a station of dipoles as a dish antenna, equivalent of a dish antenna. And then you put such stations at different distances, which could be in a Y-shaped structure or they could be in any geometry that you want, just like you would do with a dish antenna. And then you would use them in a similar fashion. I don't know if that answers the question.
Yeah. Another question is from the same person. Is the periodic array or aperiodic kind distribution of array element?
So most of the radio astronomy arrays are aperiodic. There were ones which were built as periodic with periodic spacing, and there are pros and cons for these. A periodic spacing array has what are called grating lobes. If you understand that there is a main beam, and there will be grating lobe beams whenever the phase shift is the original setting plus one wavelength or whatever. And so in some cases, those grating lobes are a nuisance. In some cases, they are useful. So all the modern radio observatories, array observatories, now use what you would call aperiodic spacings. Those are computed based on certain algorithms that where you should place the antennas in an array so that to get optimal coverage of the Fourier components that you're measuring.
Yeah. Then I have received the question that can't we use a synthetic aperture radar kind of detection to avoid the large space requirements?
To avoid the large?
Space requirements.
Space?
Yeah.
I'm not sure what is meant by that, because the two ideas are slightly different. I mean, here you need to get a narrow beam with enough resolution. And in some sense, we are also synthesizing an aperture.
Yeah.
It is just that the aperture needs to be so many times lambda, the wavelength, so that one can get the desired resolution.
Yeah.
The requirement in a synthetic aperture radar is two, I think. One, of course, the frequency is typically much higher than the kind of frequencies we are talking about here.
Yeah.
And second is that I don't think the resolution requirement is of the kind that we need over here.
Yeah. Then I would, in fact, now I am receiving one question from Professor Animesh Moitra, that how would the pervasiveness of mobile and satellite communication affect the futuristic radio astronomical observations? Any remedial measures are already taken?
Yeah, no, in fact, that's a very, very relevant question. It's a burning question, because already a lot of radio astronomy is affected by man-made signals. Like I said, that the biggest problem for radio astronomy is man-made transmissions, because as we saw that your satellite dish transmission is much stronger than the very weak signals that we are looking for, and it can easily saturate the receiver system of a radio astronomy telescope because the signal drives it into a nonlinear regime. It is so strong. And so different measures definitely are being worked on and will continue to be worked on. It's a it's a never-ending process of coexistence with all the other services that man uses. And so the steps that are taken are of 2-3 different kinds. One is, of course, some understanding of which part of the spectrum they operate and which part of the spectrum we use. Then some understanding about spatially also you can have some separation that if you're pointing in certain directions of the sky, you may be able to avoid the interference. Thirdly, there is the thing about if that interfering signal does enter, then you try to mitigate it. So one is, of course, you try to block that part of the spectrum where the man-made signal is coming from, and you block it as early as possible in the receiver chain and as effectively as possible so that it does not saturate your receiver system. Second is downstream also, if some of the weaker signals get through, then there are digital signal processing techniques to try and detect and remove them. And as long as these signals don't occupy the full time frequency space that the radio antenna is working at, it is possible to recover some part of the time or frequency space for the radio astronomy observation.
Yeah. So next question is that GMRT operates linearly at L band, different from others on low frequencies. So why?
Okay, that's a somewhat technical question. As I said, that all these radio observatories observe with dual polarization signals, which are typically either two linears or two circulars. So that means two orthogonal linears or two left and right circular polarizations. And the aim is to be able to detect the full polar state of the incoming radiation. Incoming radiation could be partially polarized, fully polarized, unpolarized. That depends on the physics of the radiating source. And often one of the challenges is to be able to detect weak polarization signals. So the sources often have only low level of polarization in their properties. And in order to detect the polarizations accurately, especially if you want to detect small amounts of linear polarization, then you need, it's preferable to convert the signal into circular polarization as early as possible so that the small gain differences between the receivers for the two polarizations, which is actually a calibration issue. If you can't calibrate the gain very accurately, then small errors in gain don't corrupt your linear signal significantly. Right. On the other hand, in order to convert from linear to circular, which you want to do as early in the receiver chain as possible, right after the antenna, feed antenna, you introduce a lossy element before the amplifier. That increases the noise temperature of the amplifier. So there's a trade-off between these two kinds of issues. And that trade-off decides whether you want to convert to circular and use it, or you prefer to observe with linear polarization and try to calibrate better in order to detect the weak polarization.
The next question is how to calibrate the phase.
Right. So I mean, that's a very general question, but I think I understand what is being asked. So normally what happens is, this is a bit like how you calibrate the impulse response of any system, which you would like to do because you want to decouple that impulse response when you are passing some desired signal through that system and looking at the output. And either you know the output and you want to know the input, or you know the input and you want to predict the output. You need to deconvolve the impulse response. So it's a similar kind of a thing. What we try to do is we try to find a source which is as close to an impulse function in the sky. That means a very small point source which cannot be resolved by the array. And you know that if that is the source, then you can predict the response. Just like if it is an impulse that is given at the input, then if you know the transfer function of the circuit, then you can predict what the output will be. So same way, if you have a very compact impulse-like source in the spatial domain, not in time, this is impulse in space, that means it's a delta function in sky coordinates, then you can measure the signal between every pair of antennas, and both the amplitude and phase of that signal can be calibrated in order to understand what is the extra phase that any antenna in the electronics is introducing. And then this can be used to correct when you go and observe the actual source of interest.
Then the question is, any plans to extend the GMRT by increasing the number of telescopes?
So there are some discussions about what we should do next after the upgrade is now successfully over and is beginning to be used routinely. Still some parts of the upgrade that we would like to finish, add a few more features and facilities. And after that, we will be looking at what we should be doing in the next round, which means, say, another 5 years from now. What is it that we should be intensely engaged in, and that we are calling different concepts are being studied, which are generally termed under the expanded GMRT. And one of the concepts being studied there is, should we add more antennas? And if so, where should these antennas be located so that we can get the maximal science benefit from locating the antennas? Right. And there are there are different requirements, science requirements. Some science requirements want more antennas in the central square to get a better sensitivity. Some requirements want antennas further away beyond 15 kilometers, which is the current extent, to get higher resolution. As you know that the further away the antennas you have in your array, the better resolution you can get. And these are different kinds of science requirements. So, but these kind of studies are going on right now.
The next question is, in classification for machine learning, from where we will get the required set of data?
That's a good one. Some of it comes from the radio astronomy data set itself as a training set. Some of it can come from simulated data, depends on the kind of application for which you're designing the machine learning tool.
The next question, I think already you have discussed, how is radio astronomy different from optical astronomy? So I am not taking this question. So you already had discussed that. So, and the next question is, are the other setups of low frequency antenna arrays in other part of the world use mesh in the dish, or is it in the case of GMRT only? How the mesh dishes work and replace solid dishes?
Okay, so how mesh dishes work and replace solid dishes is just based on the simple principle that a radio wave of a certain wavelength lambda, when it hits a surface, will be reflected close to ideally if that surface has structures which are smaller than, say, lambda by 10 or lambda by 20.
Yeah.
So simplest analogy is that if you have a ball or a marble of some size and you throw it, if it is a mesh which is bigger than the size of the marble will go through.
Yeah.
If the mesh is much smaller than the size of the marble, it will bounce back.
Yeah.
And you can make it, beyond that, if you make it solid, its efficiency of bouncing back will not change dramatically. Okay, so that is what is behind the principle of using the mesh. And obviously you can understand that if you have a wavelength lambda and you have made a mesh which is fine enough to reflect that wavelength, it is going to be cheaper than making a solid surface to do the same job. You're doing more than what is needed in order to reflect that particular range of wavelengths, but you're investing more to build a solid surface. It will have higher wind resistance, and therefore the structure required to support that solid reflecting surface will be more heavy and expensive. The motors required to drive that will be heavier and bigger and more expensive and everything. So that is the reason why 45 meter size antenna weighs only 100 tons. This size of antenna, if it was made from solid reflecting surface, would be many times more heavy and therefore many times more expensive. So since it is a low frequency radio telescope, it can do with mesh. Now that brings to the second part of the question, that there are a few other observatories which have used such mesh for working at the lower frequencies. Most of the observatories want to go up to a few gigahertz. This kind of mesh is very difficult. You can't make it work above 1.5 gigahertz, which is our highest frequency. You have to go for a much finer mesh, and then that advantage begins to sort of go away. And so many of those observatories prefer to use the solid surface and invest more money.
Yeah. The next question is, what is the noise floor level of the radio electronic system used for radio astronomy? I think this is a very good question and very...
That is, it's a good question. What happens, so what I told you there is that the typical power level is that minus 100 dBm kind of a number. And if you want to see that typical signal reasonably well, you need to have a noise floor which is significantly better than that.
Yes.
So that is what kind of sets that that limit. Finally, it is decided by the not just by the quality of the electronics, but by the fact that certain amount of noise comes in from outside, from the sky itself, and you can't wish that away. And that often then, so at the lower frequencies, the sky has more brightness and therefore more noise, and that often limits the level at which your receiver electronics needs to work. At higher frequencies, the sky noise is less, and therefore there's more advantage to build a lower noise receiver systems.
Yeah. So we also have Professor Amitabh Sen Gupta amongst us, who has listened to your webinar, and he had floated one question.
Okay.
In an antenna cluster, what is more optimum? Smaller number of larger size dishes or larger number of smaller size dishes, provided that total collecting area is the same and the spatial deployment is also same?
Yeah, so that has a reasonably straightforward answer, that if you keep the same spatial deployment and the same area of coverage, then you would like to fill it with larger number of smaller antennas. And the reason for that is as follows, that the beam width of a single antenna, as we said, is at lambda by d. And so if you have a smaller antenna, then it will see, the beam of that antenna will see a larger area of the sky at any given time. And so when you make an image with the set of those antennas, which are all looking in the same direction, that image will cover a larger area of the sky than will be possible with same total collecting area, but built with fewer dishes of larger size, because each of them will be seeing at a given time a small area. So if you want to survey the whole sky in a uniform fashion, then the array with large number of smaller dishes will do it much faster to the same level of sensitivity or noise than the array of a smaller number of dishes of larger size. Of course, the former is more expensive to build than the latter, beyond some, I mean, there are some curves which decide what is the optimal combination.
Another question which we have received, that which machine learning technique is preferred in radio astronomy, and also considering the huge set of data, how long it takes to train the system?
I can't tell specifically the first part of the question, that which of them, because I have seen myself a couple of different techniques that have been used, and I'm not an expert to be very clear about different machine learning techniques, but I've seen that they adapt some of the standard techniques based on the specific problem at hand. As far as the training is concerned, I've seen that that is not a big issue. It is like, I mean, the time taken to get the machine learning algorithm working, it is trained and ready, is much smaller than the total amount of time required for analyzing the large volumes of data that it is meant to look at. So that is not a limiting factor.
Okay. So may I now hand it over to Shogato? So Shogato, can you please ask the question to Seth?
Yeah, there is a couple of questions. First of all, can you hear me, sir?
Yes.
So first question is that, are there any signal processing or signal processing solution that can reduce the noise of the radio telescope or radio astronomy?
So there is, beyond some point, the basic noise that comes from the different parts of the electronic system, it cannot be reduced beyond some point. It is part of the data there, and you have to either reduce it directly by cooling the receiver or having better quality electronics, or you have to live with it and try to compensate for the noise by having a larger bandwidth or integrating or observing the source for a longer time. There is not much in terms of clever signal processing techniques which will, once that noise is in, that it will allow you to discriminate and remove it. That is slightly different from, when I say noise, I'm just talking about the things like thermal noise in a receiver system. Noise from interfering sources, like man-made noise or interference coming into antenna from different causes. There are possibilities of doing some smart things based on the properties of that unwanted signal to cancel it or to reduce it. But for the intrinsic noise that comes in any receiver system, signal processing techniques don't have too much leeway of reducing it. You have to either reduce it at source or compensate for it by other techniques.
Yes, sir. The second question is that, sir, why the SCA antenna is built Gregorian feet? Why not parabolic?
Right. So the wait. So the parabolic and Gregorian are not two different things. I mean, the SK antenna is also parabolic. A Gregorian is not that the Gregorian is a non-parabolic antenna. The difference is that like a GMRT antenna is a prime focus antenna where the element that picks up the signal is at the focus of a symmetric parabola.
Yes, sir.
You can think of an asymmetric parabola, which is what that in a symmetric. So you can see two antennas in this figure.
Yes, sir.
One is a symmetric parabolic thing with the feed at the center. So what happens here is the feed at the center of the dish and the supporting legs, they block some of the incoming radiation. That is called blockage.
Blockage.
This blockage is minimal in a offset parabola.
Yes.
So you can see that most of the radiation coming directly to the parabola is not being blocked, and it is like you have gone to one side where the focus is. So you can ask, how do I get the focus of a parabola to be at one side? You think of a parabola and you chop the parabola not symmetrically around its axis, but asymmetrically around the axis, and then you will get the focus to be on one side. Okay. And then after that, whether you put a Gregorian, another reflector there and bring it, that depends on how you want to have the arrangement of the feed antennas which are located there. So the advantage of making it offset parabola is the reducing the blockage. What the blockage does is that it distorts the shape of the beam of the antenna because the illumination pattern of the antenna is no longer as uniform as you would like it to be.
Yes, sir.
And so that goes into some of the technical details of the quality of the image you will get. The quality of image you will get from an offset parabolic antenna will be better than that from when you are making very deep images of very faint objects. You can understand that anything which is unbalanced, which is what offset parabola is, will tend to fall on one side. So the support structure has to be heavier as compared to for a well-balanced symmetric parabolic dish antenna. So the mechanical complexity, so if you try to make a 45-meter size offset parabola for a GMRT, it would be a very expensive antenna because its center of gravity is offset.
Yes. Sir, one fuzzy question is that, like, why not radio astronomy receiver system built in outside Earth?
Outside?
Outside Earth.
Outside the Earth?
Like Earth, yeah.
So that's what I showed you some examples. So people have started talking about, so I showed one example of an orbiting radio astronomy antenna. So One of the problems, as we saw, is that same lambda by d, the d that you require for radio astronomy, is generally quite large. Okay, so we are talking about 45 meter size antennas and spread out over 100 kilometers and 1,000 kilometers. You can't easily put that in space. Okay, and now outside means where you can put it on the moon, and that there are talks about having a radio antenna on the other side of the moon, the quiet side of the moon, the side of the moon which doesn't see the Earth. Because if you put it on this side of the moon, all our man-made transmissions from the Earth will be seen.
Yeah.
Okay. So when you talk on your mobile, that fellow will see it because the entire Earth is visible from that face of the moon. Okay. So there is talk of seeing if a large radio astronomy facility can be built on the other side of the moon. Now, if you can do that, it will be probably as good as being able to say, I can go and live on the moon. So when you reach that level of technology, you may probably have an radio astronomy facility on the other side of the moon. Because you have to go and build it over there. You have to build large enough antennas spread out over large enough distances, have the communication system to connect them up and run it and so on.
But sir, I have received another question from Professor Animesh Moitra.
Yes.
He's asking, it might happen signal level received is below the receiving system noise floor level.
Yes.
Do you use any technique similar to radiometric measurements such as that used by decay radiometer?
No. So that is certainly possible. So what happens is, like I said, finally, although there is noise in the receiver system, and that is what decides that immediate noise floor, if you take that signal, and this is true in many applications, that if there is a continuous signal that is buried in noise, there are ways to bring that signal out from the noise simply by integrating long enough, because the noise integrates differently than signal in terms of how they grow with time, with integration. Because noise is a random signal, it grows only as the square root of the number of samples that you integrate, whereas a coherent signal over the same duration of time will grow linearly with the time, and therefore signal to noise will improve as square root of the time over which you integrate that, and that can be used to and we often do that. So when you look at the immediate snapshot of the data, you will see only the brightest sources in that snapshot, because all the weaker sources will be below the noise. Now when you keep observing that patch of the sky for minutes to hours and integrate that data, then slowly the weaker sources will rise up as the noise floor will not grow at the same rate. I mean, there's different ways of thinking about it. You can say that noise falls, signal remains the same, or you can say signal grows faster than the noise grows.
Sir, I have a question. So can you please go to the slide where you were introducing SCAR?
Yeah, this one.
No, the next one, I think.
This one.
Yeah, so what I was just asking that, for example, you are having some portions of it in South Africa. Yes. The other one is there in Australia. So yes. How, and in between there is ocean, right? So yes. How this one will, the assembly will work? I am not understanding.
So it is not meant to work as an assembly.
Okay.
So as you saw that they work, those two, it's like two telescopes working at a different range of frequencies.
Okay.
There is very little overlap in the range of frequencies at which they will work. And I mean, originally the SKA was supposed to have these two ranges of frequencies, which it was known has to be built by different kinds of antennas. It can't be the same antenna which can observe all the way from 30 megahertz to 10 gigahertz. Issue was, where can you locate these two telescopes? Ideally, the search was for one single site where both could be co-located. Yeah. But in the end, two equally good sites were found, and then it became a decision that, well, we also want it and they also want it because both are equally good. And it was decided that, okay, at a little bit of extra cost, which is some of the infrastructure cost is being repeated because you have to get power to both the remote places, data connections and so on. So let us split the telescope and build it in two parts, because anyway, those two parts don't talk to each other.
Yeah. Okay. And so, Gopal, is there any other question which is coming to your window?
Yes, sir. I have one question plus last question. That is a linear and circular are useful, but why not other polarizations? Let's say elliptical. Why not?
In principle, any two orthogonal polarization states are possible. So if you want to make your life more complicated, you can think in terms of two orthogonal ellipses and design antennas which are elliptically polarized to pick up two orthogonal elliptical polarizations, and you can still get the same information at the end from it. You will have to work harder to do that.
Okay, so that's why a simpler one is go for linear or circular. It's very easy to
linear and circular, the easiest to work with, both in terms of designing the antennas as well as in the signal processing concepts involved in order to extract the final items of interest.
Right. So, sir, in fact, I thank you very much for the nice and very nice and lucid presentation. In fact, we have received several comments that which praising your one. And may I just ask, in fact, if you just allow me, I am seeing since Professor Animesh Moitra as well as Professor Amitabh Sen Gupta are here, may I just request Professor Moitra to just unmute and just give some comments for 3-4 lines?
Well, it's really nice to have them in the audience.
Yes.
Yes.
Animesh sir, if you can just unmute yourself.
Yes. Animesh is speaking now. Yeah, Animesh is speaking.
Can you see me? Can you see me? Okay, thank you.
Yes, sir.
We can listen to you. Yeah, please. Go ahead.
Yes, thank you very much, Yashwant, for your very nice, lucid talk. And I personally enjoyed very much. And I could come to know many things I didn't know. And I'm pretty sure that our young generation will be inspired by your talk and to go for, to take up some of the problems you have posed in your future, particularly in view of your spherical array problem. And I know you have an active program to involve young participants, young generation involved in your activities. And this talk will further motivate them to join your activities. That is my comment. Thank you very much once again.
Yeah, thank you. Thank you for your kind words. And you've really hit the nail on the head that for us, it is our aim is to, energize the younger generation and get them to see that what kind of interesting technical challenges and what kind of, beyond the technical challenges, what kind of things await in terms of being able to learn about the universe.
Okay. Thank you.
May I also ask Amitabh sir? Okay, Amitabh sir.
I think Amitabh sir has a problem with his mic. He writes something in the chat box.
Yeah.
So just to see the chat box.
So, yeah, but he has just conveyed his heartiest congratulations to you. Yeah. So.
Yeah. No, thanks. He is one of the. Yeah. I'm honored to have him in the audience.
Yes.
Him and Professor Maitra both is really nice that. We're there.
So. And so thank you.
Anyway, sir, so many people are writing that there's a very informative talk. It's a very useful talk. So.
So now you all have to follow it up with more details.
Yes.
Yes, sir.
Yeah. And thank you very much, sir, for amidst your busy schedule that you have agreed to come over here and give a nice presentation. And we are also it's a privilege for us to host such kind of webinar. And it's, to be very honest, it is the first webinar organized by the IEEE MTT-S student branch chapter in this this situation of this COVID pandemic. Yes. And although we in fact, to be very honest, that when you came here during the last February and delivered the talk, I myself could not be present over there because since I was the organizer, I had to rush here and there. So
that's the only good thing about the current situation, that you can get the captive audience. They have nowhere else to go and nothing much else to do, which is nice, which is really a good use of the time in terms of getting more people to be able to
Yes.
To learn, to understand about the subject matter.
Right.
Right, sir.
Okay, so since there is no further questions, so let's thank Professor Yashwant Gupta once again for having amongst us and to give some precious time amidst his busy schedule. So thank you, sir. Thank you for being here, and may I thank Shogato also for his nice moderation. Since he has also moderated from the GMRT side, that who had kindly agreed to our proposal. And also I want to thank Swapnil, that who had first proposed this one, who has first floated this proposal, that please, Shomak sir, please have a talk and please have a kind of webinar or maybe a webinar series on this radio astronomical technical things from microwave point of view. So many people don't understand this particular issue. So I told, okay, that let me talk with Shogato and let me thanks my RTS, thanks to Shogato for supporting me so much to arrange this particular webinar. Thank you, sir.
Thank you, sir.
Everybody.
Thank you, sir. Thank you so much, sir.
Yeah, sure. My pleasure. And thank you for organizing this. It's very nicely organized.
Yeah,
and you have to get the feedback as to how many people it reached. And I hope
yes.
People. Definitely, sir, we will inform you, sir.
Sure, sir.
And in fact, we are going for the recording also. So once it will be done, we will share the link with all the participants.
Okay. All right. Great.
Yeah.
Okay. Thank you, sir.
Okay, then. Thank you.
Thank you, sir.